Okay, we have been talking about refraction, the way light bends as it enters a new transparent substance. We talked about how if it goes from fast to slow, that it comes in and bends towards the normal. And we talked about how if it goes from slow to fast, it comes along and bends away from the normal. And then we talked about the extreme situation of slow to fast, that if we have a large enough angle of incidence, we can make that ray travel right along the surface of the material, and that's called the critical angle. And then we did an experiment on it, and we looked to find those critical angles. And if you have the angle of incidence greater than the critical angle, larger from the normal, then all the light is kind of totally reflected into the material again, so it cannot escape. And we called that total internal reflection. And we spent yesterday talking about interesting situations and applications of total internal reflection. So we've really talked about what happens when light enters or encounters a transparent medium. What we want to do now is we want to apply that to a very specific type of prism, because we've been using all kinds of different prisms. We've used semicircular prisms. Did we use anything other than semicircular prisms? I don't think we did. We can have rectangular prisms. They're on the cart. They're not that exciting. They're just a rectangular block. We can make prisms of any shape, really, however you want to build them, depending on what you want them to do. So we can have light encounter all kinds of different prisms. And what I want to talk about now is, and you don't write this down, you guys are quick writers, but don't write this next slide down. The question becomes, what happens if we have light encounter like an oddly shaped prism like this? And the reason I use an oddly shaped prism like this, because in the past, I've shown students what happened with a triangular prism, and I've shown students what happened with a rectangular prism, and I didn't kind of get around to that in this lesson, but it's not a big deal. But you can imagine we take a rectangular prism, and we put two triangular prisms on the end of it. And this image is not that great. My PowerPoint choked on these images, and then I had to upload it to Google, and then I re-downloaded it. So these are not exactly the way I want them to look. But if this is a ray of light coming in like this, and it hits here, this looks like it's pretty well flat. It's not exactly flat, but it's going to bend, like I said, towards the normal a little bit, which is going to be down a little bit. And then when it encounters this next interface, the normal is going to be there, and because it goes from slow to fast, it's going to bend away, which is going to make it bend down even more, all right? And so the same is going to happen on this side. When this comes along, it's going to bend towards the normal, which is going to be this way a little bit. And then again, when it encounters the normal here, it's going to bend away from the normal, and it's going to bend up like this, all right? Now, a ray that comes straight through the middle, well, how is it going to travel when it encounters a rectangular prism like that? How's it going to go? If it's straight on that prism, where's it going to go? Straight through, because it's on the normal, and that's going to go through like that. Now, what we've achieved by taking two triangular prisms and stacking them on the end of a rectangular prism is we've achieved a transparent object that can take parallel rays of light and then can kind of put them onto one spot. And we've already encountered that with reflection. What did we call it when the rays ended up all on one spot? Not necessarily, it could be an image. It could be an image, but not if they're parallel rays. If they're parallel rays, we didn't call it an image. We had a different name for it. Yeah, what do you got, Allison? The focal point. So what we can do is we can take different shaped triangular prisms with a rectangular prism, and we can get the light to bend and end up on a focal point, kind of like a curved mirror. And as we know with curved mirrors, when we get the light to behave that way, we can get some interesting images. And as you saw when I entered the room with this lens, as I said, you can get some interesting images. And it's just fun. You know what I would like to do with this sometime? I'd like to make, like a Halloween costume, cardboard box, right, some kind of thing, and then put this right in front of it, right, and do that type of thing. That would just be fun. So obviously we can see an image in there, and what we want to do is we want to be able to explain those images. So if we were to take this oddly shaped set of prisms, and we were to grind down all the sharp edges, and instead of it being made out of two triangles and a rectangle, and we made it into a nice curved surface, right, that has nice curves to it, that have kind of a triangle piece on the top and a flat piece in the middle and then a triangle piece on the bottom, we get what is called a lens. And then we can do interesting optical things with these lenses. And that's what we want to talk about today. We want to talk about how we can find images in these lenses using ray diagrams. We're going to have something called the thin lens equation. I even screwed up and called it the mirror equation on my board over there. And that's because the thin lens equation is exactly the same as the mirror equation, because the laws that govern this are very similar to the laws that govern our curved mirrors. So we're going to take all of this and now apply it to lenses. So what do I want you to write down? Hold on one second. Hold on. Yeah, we don't care about this. What is a lens? It's a thin, transparent piece of glass or plastic that has at least one curved surface. You don't need to write this. Lenses can make images that appear larger or smaller than the object, upside down, misshapen. Misshapen is if we had a lens that wasn't perfectly curved. Lens focuses light because of refraction. All right, that's pretty obvious. Let's talk about types of lenses. I want you to write this down. Just like mirrors, we can have lenses that cause light to converge and come together, and we can have lenses that cause light to diverge or spread apart. All right. You might recall that in mirrors, when we had converging lenses, what kind of mirror was it? If it was a converging mirror, what was the shape of the mirror that was converging? Anybody remember? Remember? Concave. Yeah, concave, right? The one that went in. And the mirror that was diverging was the back side of it, which was convex. Now you'll notice I don't necessarily have that written down for lenses, and I'll explain in a moment why. Because it's a little more complicated. Lenses don't just have one side. Lenses don't just have one side. Mirrors do. They only have the reflective side. But lenses have two curved surfaces. They have a front curved surface and a back curved surface. And it's the way those two curved surfaces interact that determine whether it's converging or diverging. So there's a little more detail to this. So let's first talk about converging lenses. And I'm going to draw examples of these different types of converging lenses right in the space here. And I'm going to do that when you get down to here, so I'm kind of watching what you're writing. But you'll notice in every picture that I draw that these lenses are thicker near the middle and thinner near the edges. Okay, and that's how you determine whether it's converging or not. Whether it's fat in the middle and thin on the edges. In a moment, we're going to write down diverging. I've got a diverging here, and diverging are fat on the edges and thin in the middle. Okay? So that's how you tell the difference. So we can have all kinds of these different types of converging lenses. Notice here I say double convex. That's made of two surfaces that are bulging out. Right here, and I know it's not very big, but I think you can see that it's fat in the middle. Can you kind of see that that's kind of fat in the middle? Right there, it's got some glass sticking out of it. All right? So right there, we have what is called a double convex. So a double convex looks like this, sticking out, sticking out. All right? And make sure it joins at the end there. I guess that's not great. But I could also have a convex concave. Here's an example of a concave convex converging mirror. You can see, hopefully, that it's bowed in on one side, it's concave, and it's bowed out on the other side, it's convex. And if I were to attempt to draw that, I just need to have the middle be a little fatter. So I need the convex to be a little bigger than the concave. Almost like a little moon shape there. But the important thing is that it's fat. Fatter in the middle than it is on the edges. That's how you tell whether it's going to be converging or not. Okay? And I made that pretty big. I'm running out of room for the plano convex. But that's okay. I don't happen to have a plano one. There might be one in the collection of lenses that we have. But plano just means it's flat on one surface. So we've got here flat and then convex. It could have been the other way around. And again, I don't have one here. I don't think. Here I've got a tray of some lenses. Is that flat? No, it's a little convex there. No, those are concave. Concave. So that's pretty close to being plano, flat on the one side, but it's so small it's hard to see. I can kind of feel it with my hands, but it's not a big deal. The most important thing is that it's fat in the middle and thin on the edges, and then it's converging. And its rules will behave like the converging mirrors, kind of. Okay? Now, when we draw a ray diagram, we need to represent a lens. And you can draw a big fat lens, but it doesn't serve any purpose because we really don't care whether it's one of these three. We just want to represent an image on our ray diagram that represents something that's fat in the middle and thin on the lens, or thin on the ends. And we want to be able to do it easily without thinking about it. So this is the way we draw it, and it's a double-headed arrow, essentially. It allows us to make handouts and things really easily. It's simply a double-headed arrow with the arrows pointing up and down. And what you need to imagine is that the tip of the arrow is the thin part of the edge of the lens, and the arrow that heads, the arrowhead going the other way is as if it's the thick part, but we don't draw in the thick part. Everybody kind of understand what we're drawing there? So it's like we're drawing this, without drawing that. You see what I mean? Because it doesn't serve us any purpose really to know how fat it is. All we need to know is where the middle of the lens is, and we need to know whether it's fat in the middle or not. And that image is going to do that for us. For diverging in a moment, we're going to have the arrows pointing the other way, and then the fat part of the arrows will be to the outside. All right? Okay, so that's how we tell whether a lens is converging or not by its physical properties. And I can see Megan is so stimulated by this conversation. We will move on. She was, I don't know if it was snoozing, but it was more of, no, you were disgusted with all the writing and talking that I do. So diverging, again, you don't have to write types of lenses continued to diverging. If you wrote it already, you did. That's whatever. Diverging are thinner in the middle and thicker on the edges. So here I have a couple of them. I don't know if you can see there, but that's thin there, and then there's a big thickness of glass right there on the edges. All right, just going to try to move that around. So thinner in the middle, and double concave. This is exactly a double concave. And my pen is over there. So double concave, we've got it going in, we've got it going in, and we've got it doing that type of a thing. Okay? Again, we can have a convex concave, just like I can have a concave convex or convex concave for converging. I can have the similar situation for diverging. This is trickier to draw, all right, the concave convex. I draw it by starting with the fat edges, because I know it's going to be fat. And then I draw one of the curved surfaces, like that, okay? And then I have to draw my back curved surface such that it's curved more so that it's a little thinner in the middle. So it's got to be drawn like this. Yep, go ahead. You need some tissues or are you going to make it? You're going to make it? Okay. Nothing to see here. It's okay. All right, so there's a concave convex. All right. And then a plano concave, again, flat, but it's got to be fat. So you got to have that flat so you can bring it around like that. Okay? Now, yep. It doesn't matter as long as there's one concave and one convex. Are you concerned because I have the Vex on the other side and the Cave on the other side? Would you like to flip the whole thing over? But you understand what I'm saying? It doesn't matter which one I put first. I could have drawn it completely the other way. In essence, it just means it has one concave surface and one convex surface. I had it the other way around and I had it consistent. Did I have it flipped concave, convex as opposed to convex, concave? It doesn't matter the order. It's immaterial. It's immaterial. Does that cause you stress? You can erase it and change one of them if you'd like. Not a big deal. Yep. There are no dull sides on lenses. They're all shiny.
But like, I mean, which way the light comes?
No, it doesn't, because lenses are, light is what we call a reversible, it's reversible, all right? So whether I take this diverging lens, and I can use the diverging lens, or I could even use this goofy thing. I'll use this goofy thing because it's just entertaining. Whether I hold it this way, or whether I hold it this way, you'll notice it doesn't change the image that's coming through, right? So it doesn't matter which way it is. Now, that's the same with this one. See if I've got the concave convex, and if I hold this in front of my eye, right? You can see there it's behaving like a magnifying glass, I think, right? You can see a big eye there. But if I hold it like this, it's still a big eye, right? So it doesn't matter which way the light goes through. Now, if I'm making a pair of glasses, though, and I'm putting a curve to this lens for making it comfort purposes, then I'm going to wear my glasses this way. But in essence, I could wear my glasses this way. It would still work unless you have something called an astigmatism. If you have an astigmatism, it means your eyeball has a funny shape. It's shaped more like a football than a sphere. And then your glasses have to be designed to be over your eyes in a particular orientation to make it work. So if you've got an astigmatism, you can't wear your glasses backwards. Anyway, we'll talk more about eye defects a little later on. Just before we move on and talk about ray diagrams, let me just talk a little bit about eye defects. We're going to learn that converging mirrors are also used as magnifying glasses, all right? So if you have a magnifying glass and you put it in front of your eye, right, your eye looks really big, right? You've seen that before. Certain eye ailments need converging lenses to help you see. And when you have that particular type of eye ailment and you put those lenses in front of your eyes, people who wear these types of glasses, their eyes look bigger because they literally have magnifying glasses in front of their eyes. You know, if we were going to be mean, we would make fun of these people and say they've got pop bottle glasses. I'm sure you've seen people with those types of glasses, all right? And that's because they need to use converging lenses in order to help their eyesight. If you've got a different type of eye defect, you use diverging lenses to help your eyesight. And diverging lenses aren't magnifying glasses. They actually make your eyes look smaller. See how my eyes look smaller? Okay? So when you've got this particular type of eye defect and you put diverging lenses in front of them, then your eyes look a little smaller. All right? If you need converging and diverging on each eye, then you have what are called bifocals. All right? Bifocals are I can't do it with that. If you've seen bifocals, if your grandparents or parents that use bifocals, they'll have a little extra funny little line halfway down, right? They put the converging down low on the glasses because when you typically use bifocals to look down at books, so then you look down through the converging, and then to look far away, you look up through the diverging. So that's essentially called bifocals, all right? We'll talk more about the uses of this a little later on. Notice my arrows have been flipped. If I want to, on my ray diagrams, represent a diverging mirror, I'm going to take my ruler, I'm going to draw a line, and I'm going to put the arrows like this, and that represents fat on the edges and thin at the center, okay? So that's a diverging lens. All right. So now what do we want to do? We want to talk about parts of the converging lens, and as I've done this before with you on the board, but I am going to just have you draw this. I'll describe what everything is. All right? So, and actually, I'll use the cursor to point to everything. the first thing you want to draw is the line going right down the middle. So if you've got your ruler, draw the line right down the middle. And notice it's called the PA. That's fun. We know what that is already. That's the principal axis. Somewhere in the middle, and if you don't have a protractor, we do want it perfectly perpendicular, but you can eye that up. Draw your lens up and down here, and put the arrows pointing up and down. And that's the lens. Okay? Next thing you want to do is take your ruler, all right, and you want to draw a focal point somewhere out here. Whoops, back up. You want to draw a focal point out here. Pick like 2.5 centimeters or something. Isn't that what we did with the mirror a lot? So let's use that as well. So take your ruler and 2.5 centimeters, put a spot, and call that the SF. And I'll tell you what these things stand for in a moment. Because light is reversible, 2.5 centimeters on the other side, put a second focal point and call that the PF. Is everybody catching what I'm talking about? Other side, there's actually two focal points for a lens because light can head either way. Okay? The distance from the lens to these F's are little f, and that's our focal length, just like we've had in the past. Okay? We got that down? I want you to add 2 more dots on this because we're going to be using them when we draw our ray diagrams. Even though there is not a center of curvature for a lens, in actual fact, there are 2 center of curvatures based on the concave and convex of each of the curves. Even though there isn't a center of curvature, there's still a very important point that exists 2 F distances out. So at 5 centimeters, I want you to put a little mark, and I want you to call it 2F. Is there a mathematical way to determine the 2F? For you guys, it's just twice the distance. If you take a university course on optics, you can really analyze the heck out of a lens. And I've done it, and it's not fun. And there's lots of big equations that take into account the curvature of each of these surfaces, along with the index of refraction of the glass, along with a couple of other factors in there. And if you do the math right, you can actually mathematically determine the F's and the 2F's. Both sides, 2F. Yep, it is. Both sides, correct. So, is there lots of advanced university type stuff that you can do with this? Yes, there is. I'm obviously not expecting you guys to do that type of stuff, but it does exist. All right, so you can mathematically determine that stuff. Okay, so I need another 2F on this side, just like you suggested, 2F. All right, let's now draw in 3 rays. 1 ray that's going down the principal axis, so you don't have to actually draw it. A second ray that's parallel to the principal axis. You can make that like 1 or 2 lines above your principal axis. It depends on how much room you have. It could be a half a line if you made it really tiny. It doesn't matter. I want another ray down below. And light that comes in to a lens that is parallel to the principal axis will meet at the principal focus. So the focus that's on the back side of the lens compared to the light, we call the principal focus. It's the main focus, okay? And then we have this secondary focus on the front side, all right? And they both will go through it, and you can have your arrows doing what they're supposed to do, that everything goes through. Just like for mirrors, if I have parallel rays, they will go through the principal focus, and that's one way in which we can find the focal point of a lens. The main difference between a lens and a mirror is that when light hits a mirror, we expect it to bounce back. So all of the real stuff is on the front side of the mirror. But when light hits a lens, we expect the light to go through. So for lenses, all the real stuff is on the back side of the lens, because that's where we expect light to go when it hits a transparent material. So that's the main opposite effect of a curved mirror versus a lens. For a curved mirror, the real side is out in front and the virtual side is in behind. For a lens, when light comes in this way, the real side is in behind and the virtual side is back out in front. Because we don't expect light to come back in front of a lens. We expect it to go through. That's why our principal focus is on the back side. Okay? Everybody okay with that? All right. Let's now talk about parts for a diverging lens. Now, just 1 second. You are going to draw this. You'll notice there's one main difference. Can somebody tell me what the main difference is? There's one little difference. Yep. The PF and SF are switched. All right? So draw that. You don't need the two F's on this one. Because just like mirrors, diverging lenses are not exciting in any way, right? They're always going to get us the same image. Converging lenses, though, they get us quite different images, just like converging mirrors. So the main difference is the PF is on the front this time, and the SF is on the back. And you know what? Don't rewrite the definition. They're the same. All of the lettering that we've used here is the same lettering you just wrote down. It's the same stuff. They're defining the same points and the same lines. Once we are done this, I'm going to switch to the still camera and make a movie of me drawing. And we're going to be drawing the ray diagrams, just like we did with mirrors. If you recall for mirrors, we did this great drawn-out experiment where you fired rays and found the focal point. Remember that good stuff? We could do that same experiment for lenses, but it's really doing the same thing. So I'm going to just assume that we gained enough information by looking at mirrors that we can just go straight to the rays. And you probably will tell me successfully what the rules are. Then we will be drawing ray diagrams. So if you have that handout, right, that Alana was handing out yesterday, then that's where we'll be heading in a moment. Yep. Yeah. You bet. It bends away as if it came from the PF, and that's why the PF is on the front side. Okay? Notice I used a dashed line for that, because we expect light to go through. So for lenses, when we have to find something back in front of the lens in the virtual world, it gets a dashed line, kind of opposite to mirrors. Right? Okay? With the real world being in front of a mirror, but the real world is on the other side of a lens. So same with this guy, it bends away such that it appeared to come from there, and that was terrible. I apologize for that. Couldn't use a ruler. Ugly. Okay. I'm going to, let me just freeze that so you guys can finish that. Let me just see what my next one is. Yes. So I want to I'm going to change gears here, and I'm going to put this up, and I'm getting my camera all ready. Make sure I turn it on this time. And get it all lined up. Let's zoom in a little bit. And this is going to go like that, and I got to go like this. That's pretty good. And I'm going to make a switch to this. And actually, you know what I'm going to do here? I am going to pause my movie here, because there's no need for me to have it on both. Actually, I'm going to stop it.